All right, so I think I'm recording. We're taking a look at skill packet 6, which is complex numbers, and we've in the previous video kind of discussed the an introduction to the imaginary unit and how it came about in trying to get be able to solve all polynomials. And Gauss was primarily the contributor, as I understand it, and the is credited with a theorem that is referred to as the fundamental theorem of algebra. So, pretty important and one of the most famous mathematicians in history. Now, in Skill B, we want to move on and look at these complex numbers in the form of a plus bi, and we want to be able to add and subtract and multiply and divide and more or less treat these numbers like we do any other number. That if we're given two complex numbers, we can use them to create a new complex number. So it's best understood, I believe, through examples. Now, um, a little bit of definition and technicality here up at the top. If a and b are real numbers, and you have it written, the number a plus bi is referred to as a complex number, and they'll refer to that as the complex number that is written in standard form. And what I'm going to do is I'm going to refer to a as and call it the real part of this complex number, this value b as the imaginary part, and this I as the imaginary unit. Now, it is very common in textbooks to call A the real part and to call B times I the imaginary part. So I'm separating this into three distinct parts: the real part, the imaginary part, and the imaginary unit. And technically, they want us to write our answers in that form of a plus bi. So let's take a look at some examples, and I'll point out that we're not super stringent on this a plus bi, and I'll point that out and tell you what I mean. Um, let's take a look here. We've got two complex numbers. They're written in parentheses for just ease of reading. We've got a complex number 6 plus I, and we're adding another complex number, negative 17 plus 3i. I'm fairly confident you've done this before. If you can't remember, it's really easy that you're going to treat this just like you learned with variables and like terms, that we're going to add the real parts together and the imaginary units, we're going to add those together. So we've got 6 plus a negative 17. If I don't make any silly mistakes, I get a negative 11. And if I have 4 i's and I add 3 more i's, I have a 7i. So that is written in standard form, where a is equal to negative 11, b is equal to 7, and like I say, that I is referred to as the imaginary unit. So I have written my answer in standard form of a complex number. Let's look at another example here. So we have this real number 5. We're subtracting from that a complex number, and we're adding just a pure imaginary number. You'll often see when a is of a plus bi, if that a is 0, then you'll hear it often referred to as a pure imaginary number. So again, we just treat it like terms. We're going to look at 5 minus 12 and have that be a negative 7. That negative sign distributes to be negative 8i plus the 8i. So those cancel. So when we add this real number with and subtract this complex number and add this pure imaginary number, our result is negative 7. Now, and that's going to be fine. Now, technically, if they were wanting us to write it in a plus bi form, we would have negative 7 plus 0i, where a is equal to negative 7 and b is equal to 0. But I say that's a little bit overkill. You'll just, depending on the class, that if you ever take any future math classes that you study complex numbers, you'll just have to do what the instructor has you do. So my answer for this is negative 7. So let's move on. So here I have a complex number. I'm subtracting a pure imaginary number, adding a complex number. and subtracting a real number. So it's still the same idea of like terms. We've got the 3, the 12, the minus 10. So 3 plus 12, 15. 15 minus 10, 5. And let's take a look at our imaginary numbers. Negative 5i's minus 9i's is a negative 14i, plus 4i is that a negative 10i. I don't want to make any silly errors, but it's bound to happen. Now, again, technically, this is not in standard form because they would want us to write it as addition. Sometimes you add positive numbers and sometimes you add negative numbers, where in a plus bi form, a is equal to 5 and b is equal to negative 10. Again, I'm not going to sit there and be that detailed oriented. Some people might, so I'm going to accept 5 minus 10i without any problems. And if it says that, because from there it's still easy for us to just say the real part is 5, the imaginary part is negative 10, and I is the imaginary unit. All right. Here we have multiplication, and just like with real numbers, multiplication distributes over addition or subtraction. So we can take this 6 and we'll take the first term and multiply it by 6. The multiplication will distribute over the subtraction, and we've got 6 times 3i. Well, again, if I'm not making any silly errors, 6 times 8 is 48 minus 18i. And again, I'm not going to bother with rewriting that as 48 plus negative 18i. I'm just going to leave that as my final answer. And that's fairly common. I mean, I don't. So again, when we have multiplication, just as we do in real numbers, we have multiplication distributes over addition or subtraction. So if we have 7i times a negative 12, we have a negative 84i. And now here, when we have the 7 times 8 and the I times I as I squared, we know that this is definitely, you have to keep going. You have to simplify that. This is not acceptable if it says that it wants the answer in standard form. You'll never leave your answer like this. You'll always replace I squared with negative 1. So that'll make that a negative 56. And we do put that in the first term. But like I say, I don't expect you to write negative 56 plus negative 84i. It's fine if you do, and technically that is a more correct answer, but this is fine. All right, so we have a binomial times a binomial. Some people are just going to be able to do that in their head. Other people, it might be to your advantage, and a neat and organized way to multiply binomials is to use a table. 5 times 6 is 30. 10i, negative 6i. Now here, I have negative 2i squared. But remember, I squared is negative 1. So really, I have negative 2 times the negative 1, which is a positive 2. So this product of these two complex numbers is going to yield 32 minus 16i. All right. So again, we have a binomial times a binomial. So let's be organized and do this in the form of a table. So we've got 1 times 1, 1 times I. Now here, a positive I times a negative I is negative I squared, but the I squared is negative 1, so the opposite of negative 1 is positive 1. So when I use my table to get my answer here, I notice that this diagonal, these are equal and opposite, those terms cancel, and I just have 1 plus 1, which is 2. Alright, so let's move on to the next one. So I claim that on this one, I'm going to have just a real number, that my imaginary numbers are going to cancel. So let's see if that's true, and then I'll point out to you why. I noticed that this would happen. Most of you probably already know why it's happening, but in case you don't, we've got 9 times 9, which is 81. Over here, we've got this product is 45i. This product is the opposite of that, negative 45i. So as predicted, these guys are going to cancel. Now over here, negative times a positive is a negative, but that's times I squared. So that's actually a negative 1, so this is a 25. And when we add these together, I believe that we get 106. So let's look a little bit closer at these past two. If we look at this guy, and if we look at this guy, this problem, what do they have in common? Well, it's the structure that they're written. This is written, if we use standard form, in the form a plus bi times a minus bi. And this one is as well. We've got the real part, a is 9, and the imaginary part as 5. And we've got a plus bi. So anytime that you have a plus bi times a minus bi, and multiplication is commutative, so the order that we multiply those is not important. Here we had the plus first and the minus second, and here the minus, and that commutative property, the product, multiplication follows the commutative property, that those products are the same. A minus bi times a plus bi is the same as a plus bi times a minus bi. But the important thing to notice here, that if you were to write out a table with the a plus bi and a minus bi, the i's, the middle terms there are always going to cancel. And what we're always going to get, we have a formula now, we're always going to get a squared plus b squared. So when I had this first problem, I could have looked at it and recognized that a was 1 and that b was 1 and that this is always going to be a squared plus b squared, a squared plus b squared, and 1 squared plus 1 squared is 1, and that is 2. is 2. 1 plus 1 is 2, and we get the same answer. I am listening to the Bob and Tom show, so I do get distracted with, if you've ever heard a comedian of Jimmy Pardo, he's a guest right now on there, and he's pretty funny. So we have a squared plus b squared, 9 squared plus 5 squared, 81 plus 25, and we saw that this is 106. All right, so let's real quick just simply prove it to you beyond a shadow of a doubt that if we have a plus bi times a minus bi, that we are going to get a squared plus b squared. Because if this is a times bi, a plus bi, a squared negative abi, and here a negative b squared I squared is just going to be b squared. So these terms cancel, and we just get the a squared plus b squared along that diagonal. And see, hopefully you'll be able to recognize the similarity between when we had real numbers, a plus b times a minus b, that it was a squared minus b squared. Because if you look closely here, we had the same idea going on, a squared minus b squared, but then we had that b squared was times I squared, which is negative 1, and that's why that operation of subtraction changed to addition. Alright, so I hope that helps. Let's do a few more. Here's one that students will accidentally make some mistakes on, because they'll think that this is negative 4 squared plus 11i squared. Exponents don't distribute. You really need to think of this as a binomial times a binomial. And most people are not going to make that mistake in this class, but if you're tired or in a hurry, it's possible that you might. Now this is not a plus bi times a minus bi. Oh, did I mention that that's referred to as these are conjugates of each other? These are complex conjugates. I believe that one of the homework assignments, does use the proper vocabulary and says multiplied by the complex conjugate. So the complex conjugate of 9 minus 5i is 9 plus 5i. The complex conjugate of 1 plus I is 1 minus I. So whenever you multiply complex conjugates together, you're going to get this a squared plus b squared. All right, so these are not complex conjugates. This does not say negative 4 plus 11i times negative 4 minus 11i. So that's something also to be careful that you don't change the problem. Negative times negative is positive. So if I take 16 away from 121, I get this is going to be negative 105, I think. I hope. You'll tell me if it's not. So if I haven't made an arithmetic error, I've illustrated the idea, and there's the answer there. Let's move on. So now we've looked at addition and subtraction of complex numbers. We've looked at multiplication of complex numbers. We've considered a special case of multiplication of complex numbers when you have complex conjugates and how easy it is, and it's not necessary to always construct a table in that case because the complex conjugates are always going to yield an answer of a squared plus b squared. But here we have division, and division of complex numbers is a little bit more difficult than the other operations. But it does have something that's familiar. In algebra, we often will multiply by the number 1. We've seen that a million times with fractions. If you have 1/2 and you're adding 1/3, when you add fractions, you need a common denominator. So we've looked at 2 and 3 and said we need a denominator of 6. And the idea in algebra that's used very often is to multiply by the number 1. But you don't write the number 1 just as 1. You write it as a fraction with the numerator and denominator equivalent to each other and making sure that the denominator is never 0. And over here, if I take 1/3 and if I multiply it by the number 1, but if I'm clever in how I write the number 1, we've seen now that we have a common denominator of 6 and that we've got 3 plus 2 and that, hey, 1/2 plus 1/3 is 5/6. So this idea of multiplying by 1 is nothing new, and we're going to use it here in this problem, and we're going to use that idea of the complex conjugate. See, the rule that we have with complex numbers is that we can't have an imaginary unit in the denominator. So I claim that this complex number that you get by dividing here's the numerator is a complex number, the denominator is a complex number, and we're trying to find the new complex number that you get through division of these two. And I claim that it's going to be equivalent to, in order to get that in the right form, an a plus bi form, I'm going to multiply this by the number 1, but I'm going to write 1 using the complex conjugate of the denominator. The conjugate of 3 plus I is 3 minus I, and for this to be 1, the numerator and denominator need to be the same. So it's easy for me to determine the denominator. A is 3, and there's a 1 implied in front of there. So I have a squared plus b squared. I have 3 squared plus 1 squared. That's going to give me 10. Now, I may have here in multiplying these two binomials, some of you are going to be able to do it without creating a table. Others are going to just like the organization of a table to apply the distributive property. It's a neat and organized way to do it. So I always leave this box that you can see a little bit bigger, because down here, negative times negative is positive. I know I'm going to get an I squared, and I know that I'm going to change the sign of that, and I usually just write it in the table. That's why I'm used to making that other one there so big. So I've got 12 minus 2, I've got a 10, and a negative 4i, and a negative 6i is a negative 10i. Alright, so I notice that I still have some more simplifying to do with my fraction over here. Let's continue right here. I can't do anything yet with the 10 minus 10i, but 3 squared plus 1 squared, 9 plus 1, that is 10. Well, I notice that all of these numbers are divisible by 10, that this is a single fraction, and that I can break this up into, I can take the first term and divide it by 10, and then I can take the second term there and divide it by 10, and 10 divided by 10 is 1. So I've got this written in a plus bi form. Well, technically not plus bi form, a minus. I can identify a as 1, b as negative 1, and there's my final answer. And you don't have to have the coefficient of 1 written there. That's just for visual aid. And notice that had I been going the other direction, that these two have a common denominator of 10, and that I can write these two fractions as a single fraction. So you do want to simplify these fractions. Sometimes it's okay to leave it in this form, because again, I'm not going to be super technical in making us get it exactly in standard form. We do want I and not powers of I. We do want the real part written first, or if it's a fraction in the numerator, the real part written first. But when you can reduce the fraction, as in this case, you do want to write it as 1 minus I. All right. So here we have division. We have a real number, 18, divided by this imaginary number, 5i. So again, I'm going to multiply this by the number 1 so I don't change its value. But I'm going to be clever in how I write the number 1. Now, if you want to think of 5i as 0 plus 5i and the conjugate 0 minus 5i, you're welcome to do so. It's very consistent. But when I see just a monomial, when I multiply by 1, I just multiply by I over I. Because if you put the negative 5s there, those negative 5s are going to cancel. If I put negative 5i over 0 minus 5i over 0 minus 5i, in the end I'm going to have to reduce that fraction. Well, here I may get lucky and not have to reduce it with any common factor. So in the numerator I have 18i, and in the denominator 5 times I squared. So we've got 18i divided by negative 5, and that's fine. You know, I probably, just out of habit, would probably write this as negative 18 over 5 times I, which is the same thing because that's I over 1. You multiply the numerators. All right, we've got, I think, one more. Now here, we've got a combination of operations here. We've got division in this first term, division in the second term, but then we're adding the results together. So we first want to get this first term in a plus bi form, and then in this other one in a minus bi or a plus bi form as well. Or if we could easily get common denominators, we would do that. What I'm going to do here, my plan of attack, is to take this number and multiply by the number 1, but to write the number 1 as 1 minus 2i divided by 1 minus 2i, because 1 minus 2i is the complex conjugate of 1 plus 2i. And then my second fraction over here, the same idea, but only focusing on its denominator. I'm going to multiply by the number 1 so I don't change the value. It's going to change the appearance, but not the value of the number. I'm going to have 1 plus 2i and 1 plus 2i. So I know that I don't have to make a table for this denominator, that it's going to be a squared plus b squared, where a is 1, b is 2. And here I don't need to make a table. All I'm going to do is distribute 8 to both of these terms, and I've got 8 minus 16i. Now over here, I've got 1 squared plus 2 squared. Kind of nice because I can see that these are going to be the same denominator. And here in the numerator, since I have a binomial times a binomial, I'm going to do a little bit of scratch work on the side to multiply it using a table. It's not necessary that you do it in a table. It's just, like I've said many times, just a convenient and organized way to apply the distributive property. So, trying not to make any errors here, I get 6 plus 7i if I haven't made any errors. So I have a common denominator here of 5 because 1 plus 4 is 5. I've got 8 plus 6, which is 14, and negative 6i plus 7i is negative 9i. And to me, that's fine. I would accept you leaving your answer like this. Many people, technically, if you want to get it in that a plus bi form, you take this single fraction and you split it up to 14 over 5 plus a negative 9 over 5 times I. Because now it's obvious that it's in a plus bi form, where a is 14 over 5, b is negative 9 over 5, and I is the imaginary unit. But that's fine to leave it like that. At least it's fine with me. Like I say, you'd have to check with an instructor to see. So hey, that's it for these operations on complex numbers. Sorry that I probably was a little bit long in making this with all of my additional comments, but I hope that helps, and I'll talk to you later.